In a regression problem, your AI predicts a number, not a category. How do you measure how good your model is when it predicts a number? If you build a model to predict house prices and the model is wrong, how wrong is it? So if you make a prediction of $470,000 while the true price of the house is $500,000, does that mean that the AI predicted an incorrect number? If it did, how wrong was it? How bad was it? Was it an acceptable mistake? In regression, we don't count right versus wrong. Instead, what we measure is how far off we are. In this video, we'll understand regression evaluation in 3 steps. First, we'll visualize the prediction errors. Then we'll talk about mean absolute error and root mean square error. And finally, we'll talk about an important metric called R squared. Welcome to Schovia, where we make AI concepts feel like everyday ideas. In regression, every prediction produces an error. On a graph, that error is just the vertical distance between the real point and your prediction. So regression metrics are simply different ways of summarizing these vertical distances. That's it. So let's start with the simplest metric, mean absolute error. To calculate this metric, we take each error and we remove the sign, and then we average them. The absolute here means that we don't care if we were too high or too low in our prediction. We only care about the magnitude. So if the mean absolute error is 15,000 in house prices, what that means is that on an average, we miss the price of the house by $15,000. It's interpretable and it treats every error linearly. If you double the mistake, you double the penalty. So it's simple, stable, and easy to explain. Now let's look at a second metric, which is root mean squared error, RMSE. Instead of absolute values, we square the errors. Then we average it, and then we take the square root. So why square them? Because squaring punishes large mistakes more heavily. If one prediction is wildly wrong, then RMSE reacts very strongly to it. RMSE also has the same units as the target, which means if RMSE is $20,000, your typical error magnitude is about $20,000. But it's more sensitive to the outliers than the mean absolute error metric. And if you're thinking about which one to use, a general guideline is to use mean absolute error if you want robustness. Use root mean square error if large errors are very dangerous for your application and you care a lot about them and you want that to reflect in your metric. Typically, if the root mean square error is much greater than your mean absolute error, it means that you have a lot of outliers. Before we jump into R squared, there's one other metric that professionals use when scale matters. It's called MAPE, mean absolute percentage error. Because sometimes a $20,000 mistake is huge and sometimes it's small. Being off by $20,000 on a $50,000 house is catastrophic. But being off by $20,000 on a $2 million home is not that bad. So MAPE measures error relative to the true value. It's scale aware and it adjusts the error to the size of what you're predicting. What makes it useful is when your values vary very widely, like prices, revenue, or demand. It's a good metric to keep in mind. It does have its weaknesses though. So if the true value is 0, then you can of course not divide by 0, so it can't tell you a percentage, right? Or if your true value is very, very small, then your MAPE metric can explode. So professionals usually use it when the targets are safely above 0. That brings us to our final metric, which is R squared. The R squared metric is quite different. It doesn't measure the error itself. It measures how much variance did your model explain. So imagine a scenario where you ignored all features and just predicted the average price for every house. A naive model that has some baseline error, right? Now you compare that error to your model's error, and R squared measures how much better your model is compared to predicting the mean. If your model is perfect and it predicts all the values exactly right, then your R squared value is going to be equal to 1. If your model is no better than predicting the mean value, then your R squared value is equal to 0. And if your model is worse than predicting the mean all the time, then it can have a negative value. So it means you would be better just guessing the average value for every single prediction. An intuitive way of thinking about R squared is it captures the vertical scatter of your model. If your data has a huge variation and your model explains most of it, the R squared value will be high. However, having a high R squared value does not mean that you have a low error. It in fact tells you nothing about the scale of the error. It only tells you how much variance your model has explained, not how big your mistakes are. If you care about magnitude, you're better off with mean absolute error or root mean squared error. If you care about error relative to the size of what you're predicting, then you can use MAPE. And use R squared if you care about how much of the variation in your data your model captures. So each metric here essentially answers a different question about your model and how it's making its predictions. When you evaluate a regression model, you can of course use all of these metrics. Each one tells you something different about the model. Some tell you how wrong you are, how dangerously wrong you are, how wrong you're relative to the scale, and how much of the pattern you have actually captured. If you want to see this in code, we have linked a notebook below showing you how to measure all of these metrics about your model. Thanks for joining us on Schovia Labs. Hit that subscribe button for more eye-opening insights, and as always, stay curious.